Okay, so let me just start this problem over since now we can hear us. What we're talking about is a square surface area of 2.4 centimeters squared. And it's in a uniform electric field with a magnitude of 1600 newtons per coulomb. And we need to find the electric flux through the square of at where the plane is rotated at 30 degrees, 90 degrees, and 0 degrees from it. And I drew over here this first picture, which has the plane, this one here, at 30 degrees from the direction of the electric field. And you can see that angle there, 30 degrees, is the angle we're talking about. It's the angle from the normal vector, that vector that shoots upwards orthogonally to every point along the plane. And we're going to do the same thing with this guy. This one has a normal vector here that shoots up from everyone. And the angle there is going to be 90 degrees from any electric field point. So that's 90 degrees there. We're going to do the same thing for 0 degrees. In this case, we're going to have something that's going straight up and down. And we're going to have that electric field traveling through that. And we can draw the normal vector on there. And you can see when I draw that normal vector, it's going to be 0 degrees. It's going in the same direction as the electric field is shooting out as well. So just looking at these, we can tell that there's pretty much no electric field here because the electric field, there's no flux there because the electric field doesn't actually penetrate the plane. It just goes kind of above and below because we have an infinitely small plane. In this situation here, it's perpendicular to the direction of the electric field, so it's going to have the most amount of electric field traveling through that surface. And then for 30 degrees over here, it's going to be somewhere in between there. It's going to be a little less than 100% of it, but just because it's at a slight angle. And since the electric field is traveling at a distance, there's going to be a part of the field that might make it through this this 90 degree, this 0 degree angle, but it won't make it through that 30 degree angle there. Part of that field is slipping out. So now we can do our calculations for that. The first equation is the one I like to use for this. That's the electric field times the area cosine theta. And this is for 30 degrees. So if we were to plug in our numbers, we know our electric field is equal to 1600 newtons per coulomb. And the area here is going to be, there it is, 2.4 centimeters squared, right? So that's 2.4 centimeters squared. And then we just have to do times cosine of 30. Oops, should be 30. If we plug that into our calculator, we can say that's 1600 newtons per coulomb times, I'm going to put it in 0.0024, that's meters squared, cosine of 30 degrees. And we get meters squared. Yeah. Wait, something's not. That's what I'm missing. Put my wrong units in. That should be coulomb. And our answer is going to be, that's kind of the wrong magnitude because I want my answer in newtons meters squared per coulomb. Oops. I left a few zeros out, didn't I? I converted this wrong. This needs to have 3 zeros in it. That's better. So that 2.4 centimeters squared should be 0.00024 meters squared. And that gives me an answer of 0.333, basically. 0.333. And the units there is going to be newtons meters squared over coulombs, which is our units for flux. Doing a similar calculation for the 90, that's this one here. We know it's going to be 0, but we can see it in the calculation as well. We can see that one really quickly. Right? That's EA cosine of theta. In this case, theta is going to be equal to 90 degrees. So just looking at it, cosine of 90 degrees is equal to 0. So that whole thing's going to be 0. We can plug in the numbers and figure out the answer to it, but it's really just going to be 0 either way. So we can move on to our 0 degree plane, and that one's going to be the same here, times, I'm going to write it in meters this time so I don't screw it up, meters squared times cosine of 0. Cosine of 0 is 1, so we can really ignore typing that one into our calculator. And we can get the value for this. So just copying, pasting this down here. It gives us, I put the wrong one in again, didn't I? There it is, 0.384 meters squared newtons per coulomb. 0.384 newtons meters squared per coulomb. And if we compare these two answers here, we can see that by turning that surface 30 degrees, less of the electric field is penetrating through that surface. By having it perpendicular, we're getting more of that electric field to it. And that would actually be the most, if you were to graph the amount of flux you have based on that angle, you have the most angle when it's perpendicular. And then as it gets rotated, it gets less and less until it's flat at 90 degrees. Okay, then no electric field is passing through there at all. Let's move on to another problem here. This one's similar, but a little bit different. Here we want to find the electric flux through the closed surface. So we can see we have this closed surface right here, okay, which is kind of engulfing part of this conductor. And this conductor has a uniformly distributed charge along the surface. Right? In this case, that charge is sigma, because if we remember, sigma, like orange, sigma is equal to Q divided by A, the area. So the charge that's along the total conductor divided by A. So in this case, we have this charge density going through there. And that's going to be equal to 2.0 times 10 to the negative 6. Those are in coulombs per meter squared. And to use Gauss's law for this, we have to find the enclosed area, the enclosed charge for that area. And in this case, the area they're giving us is equal to 4.0 times 10 to the negative 4 meters squared. So to find that enclosed space, we really just multiply those two values together. So I can say that the charge enclosed is equal to 2.0 times 10 to the negative 6 coulombs per meter squared. We're going to multiply that by 4.0 times 10 to the negative 4 meters squared. And looking at our units, the meters are going to cancel out. And we're going to be left with, let's do 2 microcoulombs and 4 to the negative 10. So that's 2 times 10 to the negative 6 coulombs. I don't need all that capital. Times, and we said it was 4 times 10 to the negative 4 meters squared. Oh, it's coulombs per meter squared, isn't it? There we go. So we end up with 8 times 10 to the negative 10 coulombs. So that would be 8 times 10 to the negative 10 coulombs. So that's the charge enclosed in there. But we need to find the electric flux. So to do that, we can use Gauss's law. And Gauss's law makes it really easy. Once you know the charge enclosed, we just take that charge enclosed, 8 times 10 to the negative 10 coulombs. We divide that by epsilon naught. Now, epsilon naught is equal, I believe, 8.54 times 10 to the negative 12. And I believe that's going to be in, was it Coulomb squared? Yeah, I think it's Coulomb squared per Newton meter squared are the units for that. So if we plug that into our calculator, take this value we had here. My calculator has pre-programmed in. This is using the units of farads divided by meters. Oops, that should be a divided by, and we get coulombs divided by. Yeah, we get 90.35, and this is giving me the units of meters volts, which is really the same as the flux that we have. That's 90.35. It's the same as Newton meters squared per coulomb. They're just using more of the voltage definition of the electric field units, because you might know if you had newtons per coulomb, which is the units for electric field, that's equal to volts per meter. Just another type of unit that for the same thing, basically. But this is our answer. This is the amount of flux going through this area. And we can do that by taking that charge density, using that to find the charge enclosed based on the area that we have, and then just dividing by epsilon naught. So it seems like a somewhat complicated problem at first, but it's not hard using Gauss's law. This next one's getting a little bit different. It's kind of similar, I guess, to the one that I described at first. The electrical flux through a spherical surface is 4.4 times 10 to the 4th Newton meter squared divided by coulombs. What is the net charge enclosed in the surface? So here they're telling us the flux. We want to find the charge based on that flux. So to do that, we can take our value for epsilon naught, which is equal to 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. And first of all, since we know the flux is positive and it's the electric field is going outwards then through the surface, we know the charge inside has to be a positive value, just intuitively. But we can calculate this Q because we know that's going to be equal to, in this case, the flux times epsilon naught. Just like before, I drew theta, not flux, times epsilon naught. Should be more of a, because we said before, the flux is equal to the Q enclosed divided by epsilon naught. So just a little bit of algebra, and we can switch those around a little bit. So plugging in values for that, that's 4.4 times 10 to the negative, or to the positive 4 newtons meters squared over coulombs. I'm going to divide that by epsilon, or multiply that by epsilon naught. Times 10 to the 4th. I said that was newtons meters squared over, not in there, coulomb. And that's giving me, I gotta multiply by epsilon naught times, there we go, 3.89, or say 3.90 times 10 to the negative 7 coulombs. Negative 7 coulombs. So that's the charge enclosed. Notice it's a positive number, just like we expected from our positive flux. Let's go on here. This one's the fun one. So here we have a charged sphere. The entire sphere is a non-conductive sphere, so it's the charge is going to be uniformly distributed throughout the entire sphere. The charge itself is negative 26 microcoulombs, and the sphere has a radius of 8.85 centimeters. So we want to determine the electric field due to this charge at a distance of 1.9 centimeters, 4.8 centimeters, and 25 centimeters from the center of that sphere. So we can do that using Gauss's law. And we have this 3 different Gaussian surfaces that we can make. The first one being 1.9 centimeters, which is inside the sphere. So we're only we're only enclosing a fraction of the charge of that whole sphere. The next one is 4.8 centimeters. So we're still only enclosing a fraction, just a larger fraction of that sphere. And the last one's 25 centimeters. So that's actually going to sit outside of the sphere. So we can use the idea, again, of the charge density, kind of like we did for that rod that we were looking at. In this case, it's going to be the value rho, which is kind of a 3-dimensional volume density. And that's equal to Q over V, which is the charge divided by the volume of this object itself, in this case, a sphere. And if we plug in the volume for a sphere there, we get 4/3 pi times r cubed. And notice I have a big R in this case because little r is going to be the radius for my Gaussian sphere. So as I write these out, remember that the little r is the radius of the Gaussian sphere, the big R is the radius of the sphere itself. So we can use the idea of Gauss's law here, knowing that the Q enclosed divided by epsilon naught, in this case, is going to, or is equal to the electric field times the area, right? E A, and cosine theta, in this case, it's shooting straight out from the normal vector of the sphere. That's the nice thing about spheres, is we have that symmetry. So cosine theta is always going to be 1 in this case. So I can just say it's the electric field times the area, the surface area of that sphere is what I'm looking at. So I can calculate that for a sphere. It's going to be E 4 pi r squared, where 4 pi r squared is the surface area of a sphere, and r, in this case little r, is going to be the radius of that Gaussian surface. And if we change this expression around and solve for the electric field, we can say that E is equal to the charge enclosed divided by epsilon naught 4 pi r squared. So now we have an equation for the electric field. We just have to find the values that we're looking for. And this will work for any of the 3 values, whether it's outside the sphere, inside the sphere. And so if we have 2 different conditions here, 2 different situations. One where little r is less than big R, which means we're inside the charged sphere. And in this case, we're going to have to figure out a fraction of that sphere. So we can break it down where the charge enclosed would be equal, so the Q, the total charge of the sphere, divided by 4/3 pi r squared, r cubed, divided by the total volume of that, times the volume of the Gaussian surface. And if we do that, we can cancel a bunch of values. The 4/3 pi all cancels out, and we end up with this idea that the charge enclosed is going to equal the charge of the entire sphere times this ratio of r cubed over r cubed. So little r cubed over big R cubed. So it's the amount of volume, basically, that radius cubed inside the sphere divided by the whole sphere itself. And now using that equation, plugging it back into our electric field equation up here, we can say that that electric field is going to be equal then to the charge, little r cubed over big R cubed, divided by 4 pi r squared epsilon naught. We can do a little bit of cancellation here, canceling out the r squared on the bottom and 2 of the little r's up top. We can also move that big R cubed down to the bottom to get q over 4 pi r cubed epsilon naught. And this is the formula we're going to use to solve some of these problems here, because this is giving us that ratio. Oop, there should be a little r there. That ratio between the Gaussian surface and this charged sphere itself. So now using that, looking at part A, the first part, where we had that little Gaussian surface at 0.019 meters, that's 19 centimeters. Right? Oh, it's 1.9 centimeters. That makes me feel better. And we know that big R is still equal to 0.085 meters. That's 8.5 centimeters. And we had the charge, total charge was negative 26 times 10 to the negative 6 coulombs. And still epsilon naught is equal to 8.85 times 10 to the negative 12 coulomb squared over Newton meter squared. So I just put all my variables in there. And now we have everything we need to solve this for this guy. So just plugging those values in, I know that the electric field here is going to be equal to negative 226 times 10 to the negative 6. Those would be coulombs, times 0.019 meters divided by 4 pi times 0.085 meters cubed times 8.85 times 10 to the negative 12 coulomb squared over Newton meter squared. So let's plug that into our calculator, see what we get. So like I said, negative 26 times 10 to the negative 6. That's in coulombs. I'm going to multiply that by 0.019. That's in meters. We're going to divide that whole thing by 4 pi times 0.085. And we're going to cube that. And we're going to multiply that by epsilon naught. Double check everything's right. Oh, I left off units. That's what was wrong. Units make the world go round. So our electric field at this point is going to be a negative 7.129 or 7.23 basically, times 10 to the 6th newtons per coulomb. So this is equal to negative 7.23 times 10 to the 6th newtons per coulomb. And that's going to be the electric field with a Gaussian surface at a radius of 1.9 centimeters within that uniformly charged surface or sphere. So now we got two more values to do. We can use that same formula. I'm actually going to just copy and paste so we can have it as a reference. And in this case, most of our values are the same. We still have the same Q value, which is negative 26 times 10 to the negative 6 coulombs. We have the same big R, the radius of the sphere itself, which is equal to 0.085. That's in meters. And epsilon naught never changes. So that's 8.85 times 10 to the negative 12. Be Coulomb squared per Newton squared. Newton meter squared. And finally, our little r in this case is going to equal 0.048 meters. And now we're going to plug those values into this. And this equation here only works if our Gaussian sphere is within the radius of the big sphere. So in this case it is, because this value here is smaller than that value there. So plugging it in, we have negative 26 times 10 to the negative 6 coulombs times our radius, 0.048 meters, divided by 4 pi times 0.085 meters cubed times epsilon naught. And that's going to be for our electric field, which is equal to, trust the calculator. Just going to paste this down, and the only thing that's really changing is this value here to 48, if I remember right. Yeah. So that gives us negative 1.826 times 10 to the 7. So that's negative 1.826 times 10 to the 7 newtons per coulomb. So the electric field at that point we can see is, if we compare that 10 to the 7 versus 10 to the 6, we have a little bit bigger electric field because we have more charge enclosed in it, right? So that makes sense. I like to compare previous answers and make sure that what I'm getting makes some sense. And now we get to our last size, the last radius for this problem. In this case, we can't use this one because we're not using that ratio anymore. We've got to go back to our original, this guy here. Because in this case, the entire charge is inside of it. So really, we just have to use this equation up top there. Excuse me. So doing that, we have, again, little r here is going to equal to 0.0, or I guess this is going to be 25. Yeah, 0.25. Was that 2.5 or 2.5? 25 centimeters. So I think that should be 2.5. Yeah. Meters. My brain's not working for that, right? I can never convert. Make sure I'm getting the right answer. I can just do this. Yeah, 0.25 meters. Good. So my brain is working right. So still, the radius of the sphere is 0.085 meters. Epsilon naught never changes at 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. And we have everything we need to solve this now, right? Because the charge enclosed, that Q, is the entirety of negative 26 times 10 to the negative 6 coulombs. So plugging those values in, the electric field is going to equal negative 26 times 10 to the negative 6 coulombs divided by 4 pi times 0.25 meters. That'll be cubed in this point. Or squared, yeah. Squared. Times epsilon naught. Plugging that into our calculator. Go with a negative 26 times 10 to the negative 6. Oh, wrong negative. That negative. Coulombs divided by 4 pi times 0.25 meters to the third power times epsilon naught. Did I forget something? Getting weird values. 4 pi r squared. I did to the third power again. I really want to do that. So I get negative 3.74 times 10 to the 6 newtons per coulomb. Equals negative 3.64? 74 times 10 to the 6 newtons per coulomb. So that is the electric field outside of the sphere at a distance of 25 centimeters. So you can see that the equations we need to use inside of the sphere versus outside of the sphere are slightly different. We have to then take the ratio of the sphere that's enclosed in our Gaussian surface and multiply that by the electric field that we get. And you can see us doing that right here. And then we simplified our equation so we didn't have to plug it into our calculator that whole time. And that's the method for doing that type of spherical electric field. So I want to talk a little bit now about potential energy. A little overview of that. Potential energy is really similar to the idea of work, where the negative work is equal to the change in potential energy. And when we're talking about electrical potential energy, it's really the potential energy between two charged particles. So if we have two charged particles, say one positive and one negative, we call the potential energy, say, the energy to bring in a positive charged particle from infinity to where it's at, from a distance of infinity to where it's at. So when it starts off at a distance of infinity, it has no potential energy because the equation for the force of something is equal or inversely proportional to the distance between the two. The square of the distance between the two even. So the farther away two objects are, the smaller the force is. The closer they are, the more force they have between them, so the more potential energy they have. It's kind of like lifting up a rock off the ground. It has a little bit of potential energy. When you let it go, it falls and drops. Similarly, if you have two charged particles, if they're close enough together, which all charged particles are going to have some force. It just gets to the point where you're not really going to notice the force on them until they're a certain distance close to each other. So the work done to accelerate that charged particle from rest is positive, and it results in the potential energy, basically. And we can write that potential energy formula, PE, equal to Q1, Q2 over R. So the potential energy to move any particle in there is going to be relative to the other charged particles around it and the distance between those. In this case, the potential energy is not squared like the force is because we have this distance that we're moving it to. It's kind of like the simplified version of work is force times distance. In this case, our force is the electrical force between them, and we multiply that by the distance we have to move something, and we get this potential energy for it. And the electrical potential energy is positive if both charges are the same sign. The reason being, if they're both the same sign, they're going to repel each other, and the distance between them is going to get larger and larger. So they're going to get closer and closer over time to having that zero potential energy, of having a distance of infinity between them. the potential energy of those two would be negative if the charges are opposite signs. And that's because if you have zero potential energy when you're spaced out to an infinite space, the opposite charges are going to attract. So they're actually going to go away from zero potential, getting more and more potential, getting a negative potential energy to them. So that's why we say it's a negative potential energy if the charges are opposite signs, because they're going to be an attractive force. And there's this idea that you always have a conservation of energy. In this case, it's a conservation of mechanical energy, where the kinetic energy plus the potential energy is always going to be a constant. So if your particles start out at rest, the potential energy, and you have some potential energy there, over time, the potential energy is going to decrease and the kinetic energy is going to increase to them. But the sum between those two is always constant. We always have that conservation of energy. And that's one of the universal laws of physics, is all energy is always going to be conserved. So we can look at a few different examples of this. So here's an example here where we have basically a hydrogen atom here, where it has a proton in the middle of it. Let's switch over this one. And then I got some equations for potential energy above my head there, which might help things as we go along. So we have a diagram here of hydrogen with a proton in the middle, and circling that is an electron. And we want to calculate the potential energy of an electron and proton, or of an electron and a proton in a hydrogen atom, using 1 eV is equal to 1.6 times 10 to the negative 19 joules. So we want to convert our thing to EV when we're done. And we want to use the magnitude charge on an electron and proton is 1.6 times 10 to the negative 19 coulombs. And they tell us the atomic radius, so the distance between that proton and the electron at any time, is going to be 5.3 times 10 to the negative 11 meters. That's really small. And K, of course, is going to be our Coulomb constant, and that's 9 times 10 to the 9 Newton meters squared per Coulomb squared. It's also equal to, K is also equal to 1 over 4 pi epsilon naught. So we can use this idea, because we know that the force between those two is K Q1 Q2 over R squared. But here we want to find kind of that potential energy for them. So it's that the force of them, but it's also the distance that they would have to travel. So we can say that the change in the work done by this is going to be equal. So the work to bring in an electron, if we had to bring an electron to that point and distance away from there, would be equal to K QQ Q1 Q2 over R, and that's going to be a negative work because we're moving that work away from the zero potential. Or we can say the potential energy is equal to negative K Q1 Q2 over R. Plugging in those values, so in this case, the charge for those are going to be the same value, right? That 1.6 times 10 to the negative 19. Okay, that's the Coulomb charge of an electron and the Coulomb charge of a proton, especially because we're taking the absolute value. The electron is usually going to be a negative, or is always going to be a negative charge, and the proton is always a positive charge. And we're going to multiply that by, in this case, 9 times 10 to the 9th power in Newton meters squared over Coulomb squared. That's coulombs. We're going to divide that by the distance between them. Now the distance that they give us here is 5.3 times 10 to the 11. That's 5.3 times 10 to the negative 11 meters. And this is going to equal the potential energy there. So let's plug that into our calculator, see what we get. So if I say 9 times 10 to the 9th power, I'm going to give it the units of newtons meters squared over Coulomb squared. And we're going to multiply that by the sum of the product of those two charges, which I'm just going to say is going to be 1.6 times 10 to the negative 19 coulombs squared. I know one's negative, one's positive. Once you square them, it's always going to be a positive value, right? Now we're taking the absolute value, really, so that's why it's a positive value. We're going to divide that by 5.3 times 10 to the negative 11 meters. And that's going to be equal to 4.37 times 4.35 times 10 to the negative 18 joules. And I might have to backtrack on something I said. I think the force is always going to be an absolute value, but the work is not in this case. Oh, we're just taking the negative of the work. So yeah, I left out my negative sign. That makes me feel better. So it's negative 4.34, did I say? 4.35 times 10 to the negative 18 joules. So that's going to be the amount of energy it takes, or the amount of potential energy there is between those two. But we want to find that value in electron volts, EV. So I can take that negative 4.35 times 10 to the negative 18 joules, and I want to multiply that by the conversion of EV divided by 1.67 times 10 to the negative 19 joules. That's how to convert from joules to EV. I'm just going to have my calculator do it for me. That's going to be 27. And again, this should be a negative. So going back to negative 4.3 times 10 to the negative 18, negative 27.13 EV. So that's equal to negative 27.13 EV. And that's going to be the value in electron volts. This next one is going to take a little bit longer than I have, so I'm going to stop it right here. If anyone has any questions, feel free to ask them in our drop-in hours through the Penji app just after this. I'm also going to drop in our attendance sheet for this as well. Make sure to fill it out if you're here for a class. There's the form for it there. Also check out our past videos on the Learning Center's YouTube website, and I hope to see you at future videos. Thanks for all your time.